Hello everyone, and today we're back again on AtCoder. This is AtCoder Beginner Contest 320. As always, check out the other videos on my channel. We not only do live recordings, but also explanations of concepts in programming and electronics as well. So yeah, I use the CPH Judge extension to parse every problem from AtCoder in VS Code, and yeah, we code them live. We also on Code Forces we also practice there as well, and yeah. So that's pretty much it. It starts in like 12 seconds. So yeah, any questions would be like appreciated in the comments. I always try to answer them. At the end of the contest, there will be explanations for the tasks solved. So let's go. You're given positive integers a and b. Print the value of this, but so I don't trust the power function, but I also have this already written by now binary exponentiation function, so there should be, just zoom in. So yeah, the value is binary a to the power of b plus binary b to the power of a, as far as I understood this. Okay, longest palindrome b, you're given a string s, find the maximum length of a continuous substring that is a palindrome node. There's because the string is very small, we can just iterate over all possible substrings and find the biggest string that is a palindrome. So let's just okay, so let's just read the string s. Then this is like a starting position. Where is this starting position? So the starting position goes up to s dot size. Then there is this length. So the length of the palindrome is up to s dot size minus s. And then we iterate from the starting position to the starting plus length position, divided by 2. Of course, I don't need the whole length. And then bool is palindrome. It's going to be true is palindrome is going to be also checked with s at k. S at k that is equal to s at s plus the length minus 1 minus k. This has to be all equal, and then if this palindrome answer is the maximum answer and the length of this palindrome, and then this is like the answer should be at least 1, of course, because if that's pretty much, I think that's pretty much it. Wait, here is the length should go from 1 up to the size of up to this, right? K should go up to the length divided by 2. K is length minus 1 minus this can be also introduced as s plus length should be smaller than this, right? S plus the starting position was length divided by 2. And, okay, I think that should work. Slot machine. This is an easier version of problem G. Okay. Oh, oops. Oops. That should not happen. The size, the starting position is this, then the length is this plus this. So if S is 0, the length can be at most the size of the string, right? And then this here is from this up to the length can be also as well. That doesn't quite matter. Then if the length is 1, of course that's fine. But then there's palindrome that is this plus the length minus 1 minus k. The length minus 1 minus k. So if the length is 1 minus, yeah, that should be fine. Oh, no, this is yeah, this is wrong. K is from 0 to, let's put it like this, K is from 0 to length, and then this is S plus K, and then this is of course S plus the length minus 1 minus K. Yeah, this is the correct thing. There is a slot with 3 reals. The arrangement of the symbols in the ith reel is represented by the string si, consisting of m. Okay, that's accept. Consisting of m digits. Each reel has a corresponding button. For each non-negative integer t, Takahashi can either choose and press one button or nothing exactly t seconds after the reel starts spinning. If he presses the button to the ith reel exactly t seconds after the reel starts spinning, the ith reel will stop and display t mod 10 plus 1. Yeah, okay. Wants to stop all reels so that the display characters are the same. Find the minimum possible number of seconds. So all of these reels, Takahashi wants to. She can stop each reel as follows, so that 6 seconds after the reel starts spinning, all the reels display 8. So for each of the digits, all of the reels have to be stopped at some digit, right? And then, is it guaranteed that all of the reels have the digit? This is an easier version of problem G. What is problem G? What is the difference between problem G? M goes up to 10 to the 5. And there are 10, there are these reels. Okay, so, so for each time he can press one button and do nothing exactly t seconds after the reel. So if it is possible to stop all reels, so display if it is impossible after the minimum number of seconds. So press the button corresponding to the second reel 0 seconds after the start frame stops and displays okay 8, and then press the button corresponding to the third wheel 2 seconds then 6 seconds after it's yeah. So this is no way. Okay, so it does not guarantee that all the characters exist, but all the digits. So first we have to brute force what digit we have to stop every reel. So what is the digit we have to stop it? And then kind of so because there are 3 reels, we can brute force here very easily the all of the permutations in which we stop the reel. So this is straightforward, but G is not straightforward because there are like 100 reels. Okay, so G has to do something with like Chinese remainder theorem or something like that. These are the reels, and then we can just brute force for each digit. Then we want to brute force the permutation, right? So the permutation is this. And then this is like the answer. See if the answer is int max, then it's -1, otherwise it's like the answer. And then here we say that okay, in this order we find can we brute force so what is the least time that we can find this digit? So the time is that we travel up to n. Int this is failed, so if it's failed, all the reels are spinning, right? So if reel at, so we need to do it in order, right? int the real is order at all, and then for go through the whole real and say if the real at r at I is equal to my digit. My digit is of course character here. And then we found a digit. What is the minimum time that we find a digit? So the minimum time that we find a digit is going to be equal to this. So this is the minimum time that we find a digit. So we want to iterate one more time over all of these, starting at some time. Then when we find the digit, we update the time. Okay, so if we don't find a digit, if there are no digits, so there's like count, we find a digit and we break, right? And then so this is this real. If we find all of these digits, if the count is 3, we found all these digits, we do this. But of course the time cannot be actually 1, but the time can be like +1 here and then -1 or something like this. So at the end it just doesn't count. That should be the answer. I think that should be fine. Okay, there are n people, number from 1 to n on coordinate plane. Person 1 is at the origin. You're given n pieces of information following person A's perspective. Person B, I is xi units away from in the positive x direction. And so person's AI, person BI is determine the coordinates of each person if the coordinates of person cannot be uniquely determined. So if they yeah, okay, except C, person BI is in this direction. So this is quite okay because we can just do like a BFS or something. We know for some person where that is. So there are, what is this, n and m. So n persons in this, and informations, and then informations are days. So for each information, there's a person from AI's perspective. So this is a pivot, and then there's this relative thing, and then there's delta x and delta y. And this is exactly what we're supposed to read. We can just do a read function here, and this is the pivot relation delta x delta y, and then a y dot read this. And then now the idea is just to start at position. So this is there's some position. Let's say this is the answer array, and all of these points are, there are n points, and all of them are -1 minus, not actually -1 -1. It's, yeah, so let's say that they're visited here, there, and all of them are false visited, and this here, all of them are like 0 0, and then like this, I think it's fine. Then visited at 0 is equal to 1, so the true answer at 0 is 0.00, of course that's the origin. Then there should be like a queue here. So BFS we push 0, and then for while BFS is not empty, T is BFS.front, BFS.top. Then for all these, so these are all vertices that we know relative to T. So relative to T, there should be some array for all these vertices that are relative, or all this information. So this is like pivot, relative, delta x, delta y for all of this. Relative at AI dot pivot, pushback AI, right? Yeah, so of course pivot and relative should be minus minus. Then for all of these that we say that the relative, the answer at the relative position is the my answer at T. So if visited at R, you want to can be there contradiction? All they are consistent. Okay, so there can be if this, then we want to continue. Otherwise we want to visit, so the relative is visit at my pivot plus point LL delta x delta x delta y, and then BFS dot push R as the relative point. Of course, here then if it is this now. Okay, so if it's not visited, I then want to print undecidable. Else want to print answer at I dot x, answer at I dot y. Right. I don't get it. Okay, this passes, and this says undecidable, right? Visited a team. Oh, of course, there should be also the relative position. The relative position in reverse. The reverse relative can be also achieved where this. So for relative, and then there for reverse relative is just minus here. Uh, if it's visited, or if P is visited here, that's the case, and then P is equal T times this, I think. Wait, what? The reverse, this should be swapped. This should be R. Okay, so this passes. I think all of them passes. That should pass. Let's say E. There are people gathered for an event. Okay, accepted. D accepted. So there are n people gathered for an event. The people are lined up in a row from 1 to n. From front to back. Okay. During the event, the following occurrence happens m times. At time t, a quantity Vi of noodles is flown down. The person at the front row gets it all of it. If no one is in the row, no one gets it. That person then steps out of the row and returns to their original position in the row at time ti plus si. Person who returns to the row at time. So there's like Q or something, and then from front to back. Then at time t, Vi noodles is flown down, the person gets it all. Then the person steps out of the row and returns to their original position in the row at time ti plus si. So it steps out, but then it returns back. The person who returns to the row at time x is considered to be in the row at time x. Yes, after all m occurrences, report the total amount of noodles is person gets. So, okay, at this time, we want essentially to find, to have like a segment tree, the minimum, to find always the minimum, and then have like a priority queue that will, yeah, so okay, I mean, you just want to or just have like a priority queue. Why symmetry? Like a priority queue and another priority queue, like two different priority queues. So there's operations. Each operation, do we need to save each operation or can we process it in priority queue? One priority queue will be what person is inside the actual queue, right? This is actual queue. And then there's a priority queue of the time. Outside. Then this is like inside. And then there is the answer for each of these. And then what else should there be? What time are we on? And then for each of the operations, we're going to do something here. We have T, W, and S. Okay. W is how many noodles it will get, right? So at this time T, so time T, T's are sorted. Okay, so time T's are sorted. So while outside is not empty, and outside the top dot first is what is the time sorted is smaller. Now returns a time T is considered to be a row time smaller or equal than time T, then outside dot top, outside dot top, and this person here at time T has to return inside. Push inside the queue time T dot second. So this person returns inside. Also, first we need to do each person to be inside the queue. Okay, then when these persons are done, the person that has outside the queue, that has the inside the queue, so let's talk T dot, so answer at T plus equal W, inside dot top, outside dot push T plus S, and then this is the person that has that. Then for each of the persons we have to report how many noodles he got. Wait, what? Oh, there could be 0 persons inside the queue, right? So if inside is empty, then I want to continue here now. Yeah. Okay, this makes sense. Okay, if you're planning to okay, this will be accepted, I think. Yeah. If you're planning to travel from coordinate 0 to coordinate xn on a number line, then turn around and return to coordinate 0. You can only move in the positive direction on the outbound trip and in the negative direction in the return trip. You will travel by car. The car consumes 1 liter of fuel for every unit distance it travels. You can carry up to H liters of fuel and cannot move without fuel. For all of these up to n, there is a gas station in some coordinate xi where you can get Fi liters for PIN. However, you cannot carry more than H liters. More precisely, yeah. Then determine if you can achieve the plan when you initially have H liters of fuel, and if it is possible, find the minimum amount of money required. This looks like this looks like a DP. I just don't know if it's like just some convex hole thing. So you have like the number line, right? And there is this position 0, there's this position xn, and there's some stations here. Each station is described by what? Is described by how many Fi liters can get, but where you can get Fi liters for PN. So you can get Fi liters for PIN. This is how expensive, how inexpensive or whatever that is. A liter per yen, or yen per liter. So we want to maximize this, right? We want to maximize liter per yen. Because this is very low here, can I just brute force this? Can I say that okay, I can travel to here with this cost, I can travel to here with this cost, but then there should be like liters, so there should be like dp of where I'm currently and how many liters I have here, and the transitions is where I go to some other dp here where I can say that okay, so the transition is from where I am and how many liters I have. I can go to some place, and then from this place I can charge to some how many liters I can charge up to H, and then of course travel to some other destination, which means that this should work. This should work, just straightforward dynamic programming. So this is the gas stations. How many gas stations are there though? There are n-1 gas stations, but there are n points where these gas stations. So okay, let me just see the standings, see how far behind we are. We're not that far. Not that far behind. So TP at 0 at, so this is h plus something. TP at 0 at h is equal to 0 mi, right? So now we just, oh, we have to return back as well, right? Oh, each gas station can be used at most once in total during the return trip. Okay, that changes everything. That changes everything. That changes everything. And now we have to look that up as like some graph or something. Like, because each station only can be used only once. A station can give you yeah, I see. A station is only limited. Wait, so if there are multiple stations like this, right? A station is limited to some reach, right? So from this station I can go here or I can go here. And from this station I can go definitely here, here, here. And so I kind of build like a graph, right? Then let's say this is the return. Then from return thing, I can go here, but now this station, let's say now this is a little bit different because now this is a little, actually, yeah, this is a little bit different because now it depends how many thing I have here, but oh, it's fixed according to age, so this is actually, yeah, but let's say okay, so I have some graph at back, right? I can only use a station once in this trip. What about if it's some DP, but then you kind of for the return path? Interesting, interesting. Okay, so F is this, but the G is the same as C, but you have like 100 of these, and all of them are with a huge length. What is the minimum time possible? Well, first I would think that you need to iterate over the all the digits, which digit I will fix at the end. And for each digit there is some period in which this digit happens to arise, right? And now you need to compute how you are going to use these periods. Essentially each digit each real has some of this digit that I want, right? And this repeats. And the next real, of course, also repeats. The next real, of course, also can infinitely repeat. Now you want to match somehow. Well, in the worst case scenario, all of the things are the time is, I think, very small. The answer, I think, is small. I have this feeling. First, we have to find out what the valid digits that can actually be the answer. And then the time, we can't quite apply the greedy approach, but well, if there is if for some time t there's only one choice, we definitely take that, right? That's like a greedy strategy because there's no way, there's nothing that we have to decide. But assume that there is the same thing. Since the length is the same, this here would correspond to this here. So there is some like connection. So the same digit will be in both places. When this happens, now you don't quite know which one you should take, because if you don't quite know. It could be some DP. But what if you like in a sensible way, what if you have like two reels and then you add this reel, how this reel will change the behavior of choosing on these, but it can only change things that are connected like this. So first of all, simulation is one thing, so you can simulate them. But then what do you do? When you're undecisive, what do you do? Can you brute force it? Is it possible? Well, not really. This definitely looks like a graph problem. As well, this kind of looks like Hmm. Okay, let's assume some things. First, for what problem? Here, each gas station can be used at most only once. There's some assumption here with this function. There's some assumption. Okay, so let's say this gas station, when it is used, we have some liters, and then this gas station can add on top of it. My assumption is that either you add one more charge, the minimum, you have to somehow brute force all these charges to see where it can get you up to. Not only up to what point, but there has to be a DP here. I don't think it's quite so simple. Gets you up to some other gas station with, as what we said, with some H. So DP at I with some liters L, let's say, is this, then this is some cost, right? But this doesn't assume that we have used this. This doesn't know that we have used this gas station. Now, of course, it would be way easier if the problem allowed for something like this, but to mask the gas stations, but that's not possible. So we get there, and then okay, we can reconstruct what gas stations we have used. That's one thing. We can reconstruct the solution to get to the end here. Then we could say that okay, for each of how much I get to the end, then we can, how much I have left is, so for each dp of like n and l, where l is going to change, and I'm at the end, then I can quite frankly say that how have I gotten there, right? Some other reconstruction. But not how have I gotten there, but how can I return back with some other reconstruction. What's the most optimal thing to return back to? Now it's this problem of matching the DPs that will get you there and the DPs will get you back with. But then there are multiple possible reconstructions with the same cost, which quite frankly does make the problem a lot harder. And goes up to 300, which means there's something in there. What if I say for every gas station, whether for every gas station we use the station and we get what if instead of imagining it like this, what if I imagine it as there's some stations and in the middle is this, and then that's like 0, and then that's 0, and then I can jump to some stations here, come here, and then this is my return way to home, something like this. But then each station here has to be palindromic connected. So if I use this station here, cannot use this station here. Still, it doesn't. So there is, for each station, there is this length where it can, with h thing where it can reach. This is the length, the maximum length where it can reach. And now depending on what fuel we have coming into the station, I won't come into the station if it's not necessary to. I can just skip it, not use it, just go through. But then I don't need to use the whole thing. I could use something. I could discharge my reservoir to some point until I get a cheaper station. Then I can charge my reservoir to this whole. So now my point is, okay, I want to charge at my cheapest stations. Then there's this Fi liters per PIN, right? I want to maximize this, so I will order the stations by maximum value. And I try to only charge at these stations first, the maximum value. And then I go down and down and down in value, and then try to create maybe this way. So first connect the cheapest stations if you can, and then for the return trip, no, it's too much. It's too much compute. It's too much. There has to be a simple solution here. G seems something so like Chinese remainder theorem, but so you want to not to make them all like in the same time, but to fill the time is very small because yeah, the time is very small, and we can prove that because there are not many digits to choose from. So if the time is very small, we can. How does this help? No, actually the time is not very small, but it's what if you have something like this? So what if like you have all these, let's say ones, all these ones, doesn't matter. But then like you have all these zeros and then like sometime and then one after some thousands, 10 to the 4th. So the time doesn't necessarily be very small, but there are not many choices. So if I have two strips where they match this and this, what happens is that one can be chosen right now, but the other has to be up like plus n, if that's the only thing. There could be something else here which would be faster than. So it's done. Not so much. The longest out of these four that you need to wait will be chosen right now. Then now here, let's see. Now this and this is the longest. Then this comes chosen. So imagine this not here. I think there's something else like this. And it's better to choose this than maybe as this already chose. Hmm. I don't think the time will be actually that. What if I copy them and then graphically sort them? Like for each digit, convert the strings into let's say some character, and then all let's say all these are A's, and then just one is that, and then lexicographically sort them. These ones will be, I'm not sure which, but let's say that this is the case. And then say that this is the case. All the digits are smaller than all of these. And lexicographically sorting them will just turn out to be the smallest these will be quite on the front, and then you need like a couple of copies here, like many copies. Should be fine. Like 100 copies should be fine. Let's try something like that, something stupid like that. Let's try it out, because we won't lose much here. So let me just print so it's equal to a digit, and it's the digit, otherwise it's another letter, right? That's that's 10 to the 7 already, and then that's 10 to the 9. It's so much, but I think, of course, we can optimize it, but just I'm curious if it is even possible to do that. You can maybe compress it. Yeah, let's not compress it right now and see if that's even possible. I don't think why it wouldn't be possible. I mean, I don't know if it's technically the. So essentially what they want is some what they want is some kind of suffix tree or something like that to optimize this sorting, and I would guess so. To guess this sorting suffix. Then 10 to the 5. 10 to the 5. Hmm. 10 to the 5. Is it possible that there are some convolutions involved? Convolute them all. Well, that's a huge polynomial. What does this convolution mean? It means that like where would they be, and then that would be this. So convolution will what leave? Will leave pairs where they match, right? Pairs where they all match. Pairs where. But okay, like reverse that. Do like a convolution on the polynomials where like some interesting idea, but convert them in polynomial form, right? But instead of this ones being where this element is, so if they're like let's say the string 0 is 2 2 3 3 2 2 2. Then if digit is 3, we're looking for 3 at the end, then we'll convert this polynomial like this. All of the when now is going to be consumed with going to be multiplied with polynomial 1, then polynomial 1 will make a convolution to all of these, and there will be a point where all of the polynomials contribute the shortest, the time that it takes all of them to match the convol. I would be damned if that's convolution. But the polynomials are too big. It's just too big. But convolution can be done with, like, doesn't need to be a polynomial convolution. It could be a fast subset convolution. No, not really a fast subset. No. Fast subset won't work. Fast subset won't work. It has to be this. But my okay, I don't think I have time to solve them. I have like 12 minutes left, and I won't really be bothered solving them. But I would go over all of the problems right now, and then we'll read the tutorial on F and G at the end. So okay, so let's start from the Leyland number. This I have no clue what is actually this number, but okay, that I don't know if that's, but you're given two positive integers a and b, and then you have to print the value of a to the b power and b plus b to the a power. Because b and a go up to 9, it is very you can just go and just write a power function or use the built-in power function. But what I just have a snippet with a binary exponentiation power function. Just write bin expo here. All of my snippets can be found binary expo, and just pops up the function. So all of my snippets, and this is a logarithmic function, all of my snippets can be found on the GitHub. On my GitHub, there's a competitive repository, and in this repository there is a folder with snippets, and you can find all of my snippets there. So this is a binary exponentiation function that works in a logarithmic time, but now we don't really need logarithmic time. But I use it because it's quite fast to write, like just binary a to the power of b plus binary b to the power of a. I don't trust the power function because the power function works in like floats and doubles, and precision errors can be a problem. So I don't quite trust the power function. I just write my own. Problem B, I got the wrong answer for stupid bug, but it's essentially you're given a string S, and then you need to find the maximum length of a continuous substring of S that is a palindrome itself. This problem can be solved with some kind of better approach for S if S goes up to like 10 to the 5 or something. But now, because S goes very low, up to 100, what you can do is test out for all of the substrings of S. Are they palindrome? And if they're palindrome, you just remember the longest one. You just remember the length of the longest one. So what I do is I start from some starting position, and then I try to brute force all of the lengths of these. So for length 1, for length 2, for length all of the lengths. Then I check if that's a palindrome. If that's a palindrome, then the answer is maximized with this length. So quite simple. And how you check it is s plus k is what is the k is the offset in the substring itself, and this is s plus n length minus 1. So this is from the opposite side minus k. So it has to be a palindrome itself. This substring has to be a palindrome in order to count. Then problem C. Problem C was the easy problem of problem G. Here because there are only three strings, you can brute force every digit where you want to stop all of the strings. Then when you let's say you choose that you want to stop the string at 1. So now that you want to stop the string at 1, then you can brute force the permutation in which you stop the string. And you always pick the smallest thing. But because there could be the same number in two places, like right here, you have to be careful. You have to go over the string in with a modulo. So what I do here is brute force over all of the digits, and for all of the permutations in which I try to stop the strings, then I go over all of the strings in that order. So this is the order I take them in, and then I go to find the next thing, and if the next character that is equal to D, starting from some time 0, and then you update the time to the next time, and so forth. But then you want to be careful that you found all of the separate three characters in the strings, and you just minimize the answer with some time -1, because here I do +1, and at the end it's just like one more than what you need. But that's pretty much it. It's a pretty straightforward problem, and because you try all the permutations, there cannot be any trickery here. Problem D, relative position. Yeah, so problem D is a very well-known problem. Very well-known. I mean, variations of this problem have been seen on cold forces. You want to build a graph, essentially. You want to build a graph, and for all of these n people, you have some m piece of information. These are the edges to some other person. And it says that from the perspective of person AI, person BI is this delta units on some direction. So you can see that person BI is somewhere there. So some relative to AI. But because you have to remember that AI and BI can be also swapped, so you have to test from the perspective of AI to BI, but sometimes the other way around is needed as well. So what I do here is I have a relation, one that is from the pivot's perspective, so from from AI's perspective, and then there's the reverse relation that's from the BI perspective. You don't need actually to do this. You can just use one vector and then swap these and swap with the negative sign of dx and dy, which is quite better. But I just coded this really quickly, so you're gonna excuse me the unnecessary code and unnecessary memory maybe, but still this works. So the answer is just saying that, okay, we have this is the answer for each element, but you also have some visited array, because this visited array actually says that, okay, we know about these elements, we have visited them, these persons, we know where they are, but some persons we might not have the information for them. So if you don't have the information for them, you're going to print undecidable. The information given is consistent, so you don't need to worry about if the information was given could be not consistent, then you have to check here whether this is actually consistent. But I don't check for consistency. But you start at position at this first person, this position 0, person that is in the origin, and then I do just BFS, and this BFS is essentially saying that, okay, we have some relativity to some other person. We know from his perspective where they are, but also there could be other person here, which for his perspective I know where the first person is. So from his point of view, and that's why here is plus delta x and here is minus delta x. And here we have to change also that now the pivot is the thing that we're referencing. This, I said, can be done only by just having a one radius relation, and then we can just delete this here. But okay, however, the point is it's just a BFS, and you just go over these relationships and you build up each person where they are. And then at the end, you just print them. If they're not visited, you print undecidable. If they're visited, you just print their coordinate. Quite simple. Okay. Problem E was a very interesting problem. I like these priority queue problems, where you have some n people and they are in a row, and you can imagine that the row has, like, for each person there is some space, some already predefined space, and then the first all of the persons are named are like this, are ordered from 1 to n. So each person has this space that is ordered, and then at some time t we have some noodles that so let's say t is equal 10, we get 50 noodles, or whatever that is. Quantity of 50 noodles is flown down. And then the first person, it takes these 50 noodles and removes itself from the row, so eats the noodles, and it will return back to the row after some time, let's say after some 100 seconds. Will return back. But there could be, in the meanwhile, there could be another of 20 noodles, and then these 20 noodles may be needed to be eaten after just 50 seconds, let's say. And then these 20 noodles will go to person 2. But of course you need to have another priority queue where you store pairs that person 1 will return in, what is this, 10 plus 100, so 110 seconds, and person 2 will return at 100 seconds. And this priority queue is sorted by which one returns faster, which one will return sooner. So it will be sorted by this, by this here. So this will be the first, and this will be the second. And then if now we go up to 105 seconds, now we know that this person has to return first in order, and then get the person in the queue, the first person in the queue that goes and eats the noodle. So this person might not be the first that the end might not get the noodles, but still you have to return them in the queue. And so this queue here, this priority queue, I have them in, so I have this queue in one priority queue and I have this in another priority queue. And it's quite simple. Just this is inside what are the persons inside the queue, and then outside is just sorted by time and the person. We push all the persons inside the queue and then we process each operation, TWNS. We put all of the persons that need that already ate their noodles, we put them inside the queue, here, inside this first queue. And then if the inside is empty, of course, we want to continue. But if it's not empty, we want to give that person, that first person, the noodles, increase the answer, pop them out from there, and push them in outside. And this will return after some time. He will return back. And then for the answers, just print all of the answers. For all each person will get some noodles. I mean, not necessarily some noodles, but how many noodles each person will get. Okay, yeah. So F we thought about F, but of course I want to read the editorial, especially on F and G. Now there's no editorial on F, but there's editorial on G. Also, there is just Japanese editorial here where editorials can be found as well. So in case of F, I want just to see how what's so in this problem, there is a constraint that the same gas station cannot be used on the outbound and return trips. This is the biggest issue. So instead of considering outbound independently, we can consider the behavior of each gas station on the outbound and return at the same time. The outlook will be better. Okay, the coordinate xi. So the way out g liters and on the return trip k liters. Coordinates. Oh, so you're having a DP of I, K, and J. So I, J, and K, and it's from now on. I think I can solve the problem. Note that the minimum value. Yeah. So from now on, the problem becomes quite. Okay, I think I kind of know what he's getting up to, but so there are some edge cases that have to be considered. But I'm kind of interested more in G. Consider the following decision problem: can we let all the reals display D by time t? So this is what I said. Can we do some? Can we fix this digit? But now by time t is, yeah, by saying this, okay, to this time t, can we solve that? We can solve this fast enough. We can perform binary search over this. So the decision problem can be considered as a matching problem that assigns the time to stop each reel. Consider a bipartite graph. Oh, so okay, so the time that we can stop each reel, and what is this? Okay, and then for the example, and now, okay, so this is a matching problem, but now we have to be careful with the upper bound. We can assume that each reel stop until it shows D for the nth time. Otherwise, there is a wheel violates the condition. So there's n times m. It's still what I said. This is the n times m. Okay, so this I got. Also, by the fact, we can assume. So by this fact, some fact here proposed. Yeah, we can assume that the degree of a reel is the most n. Therefore, matching problem has only n squared edges, and the decision problem can be solved in an n cube by maximum flow. Yeah, maximum flow, but so times need to be prioritized by indices or something. But yeah, so interesting, very, very, very interesting problem, and which I will want to solve. especially because it's a matching problem. Matching problems are always fun. So yeah, that's pretty interesting technique that you kind of, yeah, you do binary search over the time, but because you do binary search over the time, you don't need to prioritize times. Binary searching will give you the answer, so you don't need to prioritize times. You just need to match them. Quite a cool problem. Yeah, thank you guys so much for watching, and as always, I see you in the next week's contest. So peace.